And in this lab, I'll present to you Physics 2 Lab 5, Faraday's Law. Introduction. There are two parts to this experiment. The first part is physical experiment, where one new roll of aluminum wrap is used and a magnet, and where I determined the average time it took to fall through the aluminum wrap, which resembles a cylindrical tube with cardboard inside. I then took videos of the magnet entering and leaving the tube for trials, where I calculated the average of the time and measured the dimensions of the aluminum tube. These measurements are used later in the coding part, where I simulated the magnet falling through the tube. And the tube is simulated as rings stacking on top of each other. The result I got physical time is 1.188 seconds. In GlowScript, the result is 7 times 10 to the negative 3, which is really large difference. So this is a picture of my physical setup. I taped the roll to the wall, and I dropped the magnet through. This is the coding part. As you can see, there is magnet exiting, and it will drop from top to the bottom, and supposedly it's supposed to change color to indicate intensity of the current and the direction of the current. However, I didn't get my code to work, so that didn't happen. And with my code, I was able to obtain the graph below, where it's a graph of velocity against time. So showing parts of the code that is important. The first part is calculating the magnetic field of the magnet. Just creating the equation as we learned in class. And then we calculated flux through one ring, where later is used to calculate the flux through the whole tube. And the equation came from lecture video 43, where I was able to recreate it in GlowScript code. Same thing here, you can see the rings. So this has a while loop that executes the whole program, that before the bar magnet exits the tube, it's going to keep running. It's going to record the enter time and exit time. The gravity is always going to be the same, and calculating the flux for each ring and the current induced. And as you can see, it's supposed to change color, but that didn't work for me. So one more part I wanted to show you is the last part, where I calculate the magnitude of magnetic force on the ring and the force on the magnet. As you can see, it's still from lecture video 43. And then the magnetic force is made into a vector, where I was able to sum up with gravity to get net force. Gravity is always going to be the same, so it's always magnetic that's changing. And here we updated the velocity and position of the magnet so it can fall through, and at the end we will print out the time it took to go through the tube. The exit time didn't work out for me, but I was able to find the time myself, and then I plugged in T here. So I'm not sure, as I said, what happened, because my code did not happen to work. But if the north side is dropping down, and according to Lorentz law, the force is supposed to act up from the induced current, so it's supposed to flow counterclockwise when viewed above. When I flip the magnet, the direction of the flux, negative flux change, is different. It's actually pointing down this time. So when viewed above, it's actually clockwise. So I would imagine the magnet will fall through faster, at least a little, maybe not noticeable. So compared to my real system, as you saw in the beginning, it's really large difference. I had the magnet not being able to fall through the middle of the tube, straight down. It might be slanted, and the friction induced by the cardboard It's really different. Maybe the computational system can be made to include friction with rubbing on the wall, but that would be really hard. So the shape of the velocity versus time plot tells me that my acceleration is constant, so I would imagine that the gravity force is really strong, that it is carrying the velocity downwards and it is constant. So essentially the F net is the same throughout when it falls down, so acceleration is constant. Last two discussion questions. What if the resistivity are as close as possible to zero? Then I would imagine with the initial velocity dropping down, it's going to create a current really large that you will be able to float the magnet essentially in the middle of the tube against the gravity. So what if holes and slots were cut into the tube? I would definitely imagine the magnetic induced current is gonna be flowing differently, so that means the field is gonna be different, and that would definitely affect the ring currents, because now you can't model them as rings if you have holes or slots in there. So that's my presentation. Thank you for watching.